Kepler proposed that planets revolve round the Sun in elliptical orbits. Thus, his model deviated from that of Copernicus, which mentioned circular orbits. He compiled 3 laws about planetary motion. First law, law of orbits. All planets revolve in elliptical orbits with Sun at one of the foci. An ellipse has 2 foci. If we consider any point on the ellipse, the sum of the distances of the 2 foci from the point is always the same, whatever is the location of the point on the ellipse. The animation shows the elliptical path of a planet around the Sun. You can draw an ellipse easily by considering any 2 points on an axis. These 2 points are the foci. Place 2 common pins on the foci. Tie 2 ends of a string on the pins. Pull the string taut using a pencil. Place the pencil on the sheet and move the pencil as shown in the animation. Your ellipse is ready. In this schematic diagram, AP and BC are known as major and minor axes of the ellipse. If O is the midpoint of AP, then AO equals OP is known as semi-major axis. In this diagram, semi-major axis equals A and semi-minor axis equals B. Circle is a special case of the ellipse, when the 2 foci merge into one point, namely the center, and the semi-major axis becomes the radius. Second law, law of areas. The imaginary line joining a planet and the Sun sweeps equal areas in equal intervals of time. In other words, the planet covers larger distance in its orbit when being near the Sun than when being far. This is the reason why planets which are farther from the Sun seem to move slower. Let us study the law in detail. Consider a planet of mass m and velocity v orbiting the Sun. Let r and p be its position and momentum vectors. Area swept out by the planet in a time interval delta t is given by delta A is equal to half r into d delta t. Hence, delta A by delta t is equal to half r into p by m, since d equals p by m, which is equal to L by 2m. In the above equation, L equals r into p is the angular momentum of the planet. As the gravitational force is directed to the center of the Sun, along r it is a central force. When an object is subjected to a central force, its angular momentum L is constant. Hence, as L and m are constants in the above equation, the left-hand side, namely delta A by delta t, is a constant. This is the mathematical form of the law of areas. Third law, law of periods. The square of the time period of revolution of a planet is directly proportional to the cube root of the semi-major axis traced out by the planet. The table contains approximate values of the time periods t and semi-major axes a of the 9 planets in our solar system. The quotient q equals t squared by a cubed is the constant of proportionality.